right triangle. I'm not going to spend much time on that because I think everyone is familiar with it by now. The main thing is that basically factorization properties of scattering amplitudes, when we go in the zero energy limit of, for instance, an external graviton, has been shown to be equivalent to a set of conservation laws of this infinite number of charges, which are associated to an asymptotic symmetry group. And just to be clear, all the statements I'm going to make in this talk refer to the massless tree level and no logs case. We heard a lot about logs. It's a very interesting story, but as we will see, the mixed helicity sector is complicated enough. So for the moment, I do without logs. And so, of course, since the establishment of the first correspondence, then there's been a very interesting interplay between symmetries and amplitudes calculation. The first realization of that was that since there was already an extension of super translations by the time that this correspondence somehow was established, then people wonder if there is a new soft theorem associated to this extension that Glenn and Trossard proposed. And there was one, and this one revealed the existence of a further subleading soft theorems. And then, of course, the question was, is there a class of symmetries that corresponds to this sub-subleading soft theorem? In this case, it was quite tricky because these symmetries are not standard symmetries, are like local symmetries generated by pseudo-differential vector fields. That's why it took a while. There's also a relation in terms of overleading vector fields. The nice interplay is that while the first there went in this direction, there was also kind of a feedback because what we found was that there were also some collinear terms coming up from basically the Einstein equation for the spin to charge. Then eventually, very recently, these two people went back to and computed from the amplitude side, and they seem to find some matching. So, but anyway, this whole business of correspondences is what get the celestial holography started. And celestial holography is this reformulation of the scattering problem in a basis of asymptotic boost eigenstates. And in a sense, if can really be characterized, many results are characterized by this log, and that for the directions of null momentum, really on this basis, really corresponds to the positions on the sphere from the celestial point of view. Now, what I want to stress is that there is really a central role played by symmetry as an organizing principle for observables both in classical and quantum gravity. And in fact, the asymmetric scattering amplitudes can be recast in celestial holography. They'll be recast as correlation functions of SL2C primaries, where that is identified by these operators that depend on the conformal dimension and the 2 points and the 2 coordinates of a point on the sphere. The plus and minus here refer to the helicity. And then the OPE data of the celestial CFT encodes the behavior of the scattering amplitudes in the collinear limit. So this correspondence between this, as was mentioned before, these null directions and point on the sphere somehow allow us to import results from the momentum basis, in particular the universal behavior of the collinear limits of the amplitudes, into the OPE. And then the question is that if we can, the goal, the dream in a sense, would be to find a celestial OPE for any three-level scattering amplitudes using symmetries. Now, how would this work? Well, the idea is that correlation functions should carry the representation of the full corner symmetry algebra. And the action of this corner symmetry group on these asymptotic particle states generates, can be expressed in towards identity, which arise from the soft theorems, and then this lead to recursive relation for the OPE data. So the hope is that these recursive relations are somehow strong enough, or useful enough at least, to fix the OPE coefficient. And a very nice implementation of this idea happened basically for when we studied the OPE for two conformal primary gravitons, where basically what happens here, a way to derive at least this OPE is to say, okay, I just do the Manin transform of the leading term in the momentum space basis, which I know is the universal term. This would give me the primary, so the n equals 0 of this OPE, and then I implement a SL2 symmetry and as a set of recursive relations to fix these coefficients, and this introduces all these descendants and determines this beta function here. And once this LP was written down, then people realized that there is, in fact, a W1 infinity symmetry, which is associated to this OPE. And that's how this W1 infinity plus 1 plus infinity entered the stage in celestial holography. So moreover, if you compute the OP between gravitons and other celestial prime operators associated with massless particles, you see that they transform non-trivially under this representation. So we see already there is a very important interplay between symmetries and CFT data. Now, so this was done from this OP point of view. Now the natural question was, since we know the Einstein equations somehow are a statement about a representation of the coordinate symmetry algebra, is there a space-time gravitational phase space interpretation of these higher spin symmetries? And I will review a bit more in detail this, although we've already seen it in several talks. But that basically what we did with Daniele Laurent was to propose this set of higher spin charges that satisfy this recursion relation. These are the exact Einstein equations up to spin s equals 3. And one can see that they are associated for higher spin to non-local symmetries generated by this kind of pseudo-vector fields. And from this recursion relation, then you can show that there's a very important, which I'm going to come back to this point, which is crucial for the rest of the talk. In fact, that the action of the quadratic, so when you solve this recursion relation, you get a soft piece and a hard piece, and then all based on the spin, you can get all power up to s plus 1 powers of fields in the expression of the charge. But if you look at the action of the hard charge on, for instance, the asymptotic shear operator, this will produce exactly the OPE between the soft charge and a conformal primary graviton in the celestial CFT. And the second result, using this action, then you can show that the algebra of these charges, they satisfy this, they represent this W1 infinity loop algebra in the gravitational phase space. Of course, then there's been a lot of evidence for this algebra coming from Betwister string and self-dual gravity for space that we heard quite a bit so far. Also, there's been a non-perturbative nether realization of these charges in a recent work of Laurent with Nico. But I want to now, there are two open issues that I want to address. From the celestial CFT side, we know that when we solve the massless Klein-Gordon equation for asymptotically for the flat four-dimensional spacetimes, there are two classes of solutions that transforms into the highest representation of SL2C. The first family is the usual one that we use to build the standard basis for conformal primary wave function. And it has a local nature. And the OPE is in direct correspondence with the collinear limit of the scattering amplitudes in the momentum space. But there's also a second family, which is associated to the first one by a shadow transformation. This provides an alternate highest weight basis, but it has an a priori non-local nature, in the sense that the location of the celestial operator on the sphere, it doesn't coincide anymore with the direction in the bulk of space-time that I was mentioning before. So this makes things quite cumbersome, and also like the physical understanding of what these operators really mean. It's not clear. In particular, you see this is the shell transform, and on the 2D sphere that it's written this non-local way. There's this integral over the sphere that and depends on these weights h and h bar, and these objects shift basically the weights h and h bar of the region operator to 1 minus h and 1 minus h bar. At the same time, we know that this object actually play an important role in CFT, in particular in celestial CFT. The stress tensor of the celestial CFT had been constructed starting from the shadow transform of the subleading conformally soft graviton. And it has been shown in these papers that it has actually a local action in the OPE. So there is clearly an important role played by these shadow transforms. And the question is there like a meaningful notion of OPE for the shadow states due to the fact that the coincident collinear limit now doesn't, we lose the concept of coincident collinear limit. So is there a meaningful notion of OPE for these states? Some of this question has been addressed partially in the literature so far. There is this paper here, which only recently I became aware of, so I don't really understand much what they do here. But more recently, there is this paper by Monica and Mina, which I met them in New York in April, and we started talking about shadow transforms, and they were telling me that they were actually trying to understand how to construct OPE for shadow states. And that very much resonated with me because, as I will tell you in a bit, the shadow states appear in a very surprising way when we move to the next open issue. Also, somehow related to this notion of OP for shadow states is the notion of double soft limit in the mixed helicity sector. And these two are, it might not appear related, but in fact, I'll try to show you why there is, in fact, actually correlation between these two open issues here. So this is from the CFT side, and as I was mentioning, from the gravitational phase space side, we know that there are these two copies of LW1 infinity. So the bar charges here are the opposite helicity charges. So between themselves, they close this beautiful algebra, but people somehow it has been swept under the rug what really happens when you go to the mixed helicity sector. And in order to really call it, I mean, in the self-dual gravity, this problem somehow we know how to compute this bracket from crystal space, but from the full gravity point of view, in the gravitational phase space point of view, this is an open problem. And of course, it would be very upsetting if somehow this beautiful symmetry is broken, at least in some, I mean, fully broken in a sense, or if there are some sector of the theory where we can actually make sense of this commutator. So this is important also because, I mean, the reason why.
So, but you mean at quadratic order as well, no? Because also the previous two commutators are true only at quadratic order, no? The previous two brackets.
Yeah, so as we will see, this has been proven up to quadratic order. This one already at linear order. We don't know really what it is. Okay. The importance of this mixed sector is because, of course, I mean, in the end, we want to connect with observables, and that's why we need the real symmetry generators to study, for instance, possible gravitational wave deviation from parity violation effects, for instance. Also, this were mentioned by Mark the other day about this reconstruction of a signal from the bulk using this multipolar post-Minkowski metric expansion. Seems that requires the understanding of this mixed helicity bracket. Again, I guess it's really because to the fact that we want to eventually talk about real generators. So there is, beside the purely, aesthetic reason, in a sense, there is an important reason to study the mixed helicity sector. Okay, so the outline of the rest of the talk is I'm going to review how to construct these high spin charges very somehow quickly, and I will show you the construction in the same helicity sector, and then I will move to the mixed helicity sector, and we will see how shadow charges appear when we go to the mixed helicity sector. And then I will, you can do the same story for Yang-Mills, and in that case, I will give you some examples of how to use the mixed helicity bracket Yang-Mills to put some constraints on the celestial PE for shadow operators and relate to some of the results that Monica and Mina have showed in the paper I mentioned before. Okay, so let me quickly go through the gravitational phase analysis. Well, we start with the usual decomposition with the bonding metric written in these bonding gauge conditions. We've seen this already plenty of times, so I won't spend much time. We impose some generalized boundary conditions that relax a bit the original BMS boundary conditions. And then you can expand these coefficients that appear in the metric here. So this phi here, the epsilon A and the gamma B. And what you realize is that at 1 over R, order in each of the metric components, you get objects. So this is the bonding mass. This guy is the covariant angular momentum, and then you realize that also order 1 over r, don't get fooled by this r to the third because there is an r square here, so this is still 1 over r. There is an object which is called TAB, which is a spin-2 charge. And then, of course, there are the free data CAB. Now, I just give you basically the what else could it be story here. So this is not the way how we came up with these higher spin charges, but if you, after you spend a lot of time doing calculations, you realize, okay, what else could have been these higher spin charges? And of course, since you're looking for object that transforms covariantly, it's the natural place to look is biscalars. So let's talk about biscalars for a second. You introduce, we saw this before, an holomorphic frame on the sphere, which allow you to rewrite the metric and the volume form on the sphere in this way. And then you can basically use this holomorphic frame to convert spin tensors, tensors into scalars where you replace the spin S with the helicity on the sphere. So you start with the tensor, symmetric traceless tensor, for instance, here with the S indices. You contract them with these holomorphic frames. If you associate a given helicity to the M and the opposite helicity to the M bar, then you can convert these tensors into scalars, and this S here is the helicity of the scalar. So now you have two labels, it's the conformal weight and the helicity. And then you complete null frame with these extra two fields to compute the wide scalars. And again, assuming that there is Peeling theorem is valid and null infinity, this is the expansion, a leading order of these scalars. And this is going to be the object where all these higher spin charges lie. So what you do is you can, so for spin that goes from -2 to 2, these are the leading order pieces in the biscalars, and these are exactly the charges. So for instance, psi 4 contains the time derivative of the news. Psi 3 is this energy current, which is some double spatial derivative of the news. And then at spin 2, you have psi 2, you have the spin 0 charge, this is a complex mass. Then you have the angular momentum and this spin 2 charge. So this is all the leading terms. And then you can expand the subleading terms of psi 0, and you see that basically you can decompose at each order n, there is a global piece here and a local piece. So what I mean by global and local means that these objects basically live in spaces that are spanned by spherical harmonics. So if you have these are all spin 2 quantities, so they live in the vector space spanned by harmonics of S equal 2, and then you have L that goes from 2 to infinity. So there is a piece which has a finite number of L's, which is this one, this decomposition here that goes from basically from 2 to n plus 2. And this is what I call the global piece. And then there is all the others, angular momentum variables, values higher than n plus 2. And these are infinite dimension. These are the local piece. So this is where the Newman-Peros charges live. And then there are these extra terms, which is where these higher spin charges live, because they all take this kind of form here, plus ... which are corrections that appears at higher spin. And again, from the Bianchi identities of this at each order, you can see that these charges defined in this way as this term that appear as derived n times inside the leading term of psi n 0 satisfies this recursion relation for spin s bigger than equal than -1. So this recursion relation is exactly verified to all orders up to s equal 3. And if you just look at linearized theory, it's also an exact Bianchi identity for all spins. Okay, I guess we've seen this before. Then what you do, you need to impose some boundary conditions. In particular, you want to integrate those charges over Scri, so you assume that you end up with derivative vacuum at Scri plus. And in order to make them U finite, you also need to assume that it's an radical quantum space at U plus minus, which allow you to write these charges and it's an integral over Scri. And you need to do this renormalization procedure to make them U finite when you go to U minus infinity. In this way, you can define these charge aspects as the limit of u going to minus infinities of this linear combination of these charge aspects that I introduced before. And you can look at the linear part of these charges when you solve the recursive relation, and this is the linear charge. So this NS is in our convention, this is a negative helicity sub S leading of graviton theorem operator, and then you have the quadratic term that takes this form here. Okay, so this is so now you can go on Scry and use the radiative phase space to compute the action of this quadratic charge, for instance, on this soft conformal gravitons, and you see that the action that you get from the hard charge is exactly the OPE that you would get from celestial OPE, the one I showed you before, if you take this double conformal soft limit on those two conformal primaries. You get the graviton here, the conformality of graviton. You get another conformality of object here, which you derive with some special derivatives and gives you the soft charge. And this quantity here is exactly this quantity here. So this is basically the soft factor at leading S or S. So there is this correspondence between the OPE and the action of the hard charge that is basically a statement about the soft theorems. Now, and then of course the word identities for these high spin charges give you this tower of 3 levels of gravitons theorems. Furthermore, then you can construct charges by integrating these aspects on the sphere. And using that action on the news and on the shear that I showed you before, you can compute the algebra. This is only at the linear order, but you can also do it at the quadratic order. And that's how you get the W1 infinity. So this is a story that I think more or less we are familiar with. Now let's move to the mixed helicity sector. Are there questions so far? Yeah. This is the shear.
Okay, so essentially all the nonlinearities can be packaged in the form of C times the charge, is that right?
Yeah.
Okay.
Yeah, when you solve recursively, you have like the leading term in the shear here, combined with this, give you the quadratic order in the Q S minus 1 and so on.
Okay, so you're saying up to S equals 3, this captures all the cubic terms and all the complicated things. Okay, great.
Yeah.
Thanks.
Yeah.
So just to have an idea for the values of S bigger than 3. So what is more or less the form of a correction? So
you will have terms which mix helicity. So you see in I think I showed here. Here you only have in the quadratic order, for instance, these two objects have opposite helicities. You have one C as one helicity and as an opposite one. Then if you go to higher orders in spin S equal more than 3, you only have one C and powers of the fields of the other helicity. But if you go above 3, then you will get terms which also contains more powers of the opposite helicity term, for instance. So you have terms that, the structure has somehow the mixes helicities in a much more non-trivial way.
Okay, so in the equation that you are showing explicitly, there are only terms of a single helicity, and the extra correction mix them.
Yeah, the extra correction would introduce, there would be commutators between charges of mixed helicity. I mean, there would be products of charges of mixed helicities at higher powers and so on and so forth.
But still, you expect to be able to rewrite the equations of motion only in terms of these charges. So it's just that you have horrible products of these charges. So nobody knows.
That's a very open question at the moment. Okay, so the mixed helicity sector. Let's start. So we can do the same thing. We know the action of the quadratic charges on the shear and on the opposite helicity of the shear. So you can compute the linear order bracket of two opposite helicity charges with general spin. And what you get, I mean, this calculation, it's really not difficult in the linear order. You get this quantity here. Now, this looks quite messy, but just to highlight the problem here. So what you expect, you should get a linear charge on this side. Now, a linear charge, either if you take the q bar or the q, what it has is, if a spin s, as either s plus 2 derivative or s plus 2 conjugate variable derivative, okay? And the reason why you are in trouble is because since this object contains both d and d bar, you get combinations, powers of d and d bars, but not enough, neither of d or d bar, to reconstruct this total derivative here. So you can see, like, in each case, you have only s plus 2 d derivatives here. The others are d bar. So you're not able to reconstruct the linear charge. This is really the obstruction to close this bracket. And so you can, what you can do, I mean, we realized this long ago. We just, okay, let's go back to that eventually, but it really bugged me for a while. So then I remembered that there is actually something that, you know, takes d derivatives into d bar derivatives. And in fact, what you need to do is to remember that there are celestial diamonds where edges of the diamonds really corresponds to powers of z bar or z derivatives. And you can go from, you can convert, in a sense, z bar derivatives into z derivatives by doing a shadow transform. So this is, okay, this is basically, so this is a celestial diamond for when, in the case where the spin is bigger equal than, I don't know if I say it, yeah, bigger equal than 3 in this case. What you have here, this is the soft graviton that I introduced before. Then if you take z, 2 plus s z derivatives, you end up with a soft charge that also I showed you before. Now, if you do instead s minus 2 z bar derivatives, you end up with an object which is the shadow transform of this charge here. So you can go from, you can show that this going up and down these edges really corresponds to do a shadow transform. And then you can continue along the edges of the diamond, and what you end up with is a quantity which is not really the shadow transform of the soft graviton, but it's what we call the dual soft graviton. So keep in mind that the relation to go from one point to the opposite one, what you're doing is like in terms of h and h bar, you're changing the weights in this way, or if you want, you go from delta to 2 minus delta and s to minus s. Okay, and the same, I mean, if you do this, you see the weights, that applies also to these 2 points, but these 2 points are not really a shadow transform of one of the other. So this looks like something we could use to write the right-hand side of what I showed you before in terms of a charge. And so what we did was, okay, let's define shadows aspects. So using the diamond, I can define this the linear soft charge, the shadow of the linear soft charge, as this d bar s minus 2 of the soft graviton. Also, I can invert this relation, again, using the diamond in this way here for spin s. So the diamond changes if you are in a s bigger than or equal than 3 or s smaller than 3. Basically, what happens is that these 2 points interchange each other, and these 2 points interchange each other. So what happens is that now the soft graviton, which would sit here, is really the shadow transform of this object, while the charge would be the dual of the other charge, but they're not directly shadow transform. So you have to be a bit careful when you have to consider both cases, s bigger equal than 2 or s smaller equal than 2. When s is equal to 2, the diamond collapses, so it doesn't really matter. And that's why the relation between the q tilde and the soft gravitons are a bit different in the 2 cases. And you can define, then you can use this shadow aspect to define soft shadow charges with some parameters tau tilde, which now have to live in this representation delta equal 3 and s and j equal s. And this q tilde would have delta equal minus 1 and spin s helicity j equal minus s. So it still like gives you the combination where the total object has delta 0, delta 2 and spin 0. And then this object can be defined introducing this propagator here. So this Gn is a propagator that allows you to invert n power n powers of the derivatives. And define, again, using the diamond, you can define the q tilde in terms of the original q's for spin bigger than 3, or for the opposite case, you have 2 propagators that you need to put in, and you can invert the acceleration again in the 2 cases. So this is just these propagators that appear. And the same thing you need to do for the parameters. So you can introduce shadows for the parameters, S and S bar. So what I mean by shadows is that these are really the shadows where S is bigger equal than 3. When S is more equal than 2, this is not really the shadow, but it's the diamond I was saying before. There is this duality pairing that you have that is not really the shadow, but it does the same switch of weights. So these objects are no local now parameters that you need to introduce, and their inverse as well are useful. So now I flash them, but don't worry, you can derive all of this just purely from the diamonds and from the definition of the shadows. These are the relation. You need these maps and the inverse maps. And if you reduce to, so for spin bigger equal than 3, as I was mentioned before, these are nothing else but that the usual shadow transforms. And in the flat case, this propagator is what you probably used to, is the standard, takes the standard form here. So with this definition, then you can see that the original charge, the soft charge, can be written as a shadow charge of a parameter which also has to be acted upon with this S tilde map. So you have 2 kinds of maps that are acting in this in here that gives you back the original charge, and the same for the bar. But then what you realize is that actually the shadow charges can really be written in terms of the original charge, where the parameter now is shadowed. So you can basically shift the shadow from the aspect to the parameter and use all the commutation relation of the aspects that you had before, but now the parameters are no local. So this is really the key technical point, that the shadow charges can be written in terms of the same aspects, but with a shadow parameter. So then now you can compute the algebra in a straightforward way. And for the mixed helicity sector, okay, this looks quite nasty when you can express the bracket in terms of these charges, where now the tau 1, 2 parameters have this non-local structure given by these maps here. But the real ugly thing is that these phi's are not total derivatives. So this makes it very ugly. But what you can realize is that you can turn this into total derivatives if you restrict to the wedge condition. So if you take one of the 2 sectors to satisfy the wedge condition, then that mixed sector helicity bracket at the linear order becomes much nicer. And you see, you start recognizing a pattern that looks like what we had for W1 infinity before. The only difference is that, of course, we have these inverse shadows of the parameters, the original parameters that we have in the bracket, in the bar charge here. And then there is also a shift of weights. Instead of having S1 plus 1, there is an S1 minus 3 here, which is a natural shift simply because now this object, this Q bar, has an aspect that has a conformal dimension that has been shifted with respect to the original one. So I mean, I can explain you better if you're puzzled by the shift, but it's the natural shift that actually you would expect just based on purely what you would expect from the action of the Virasoro action on these charges. So this shift here, it's totally understood. It's not suspicious. Or if you want to rewrite more, so if you define the charges as the sum of one helicity and the opposite helicity, and you compute the bracket, you see you get, in this case, since I put the global condition only on the taus, I get a tau bar, which has this extra component here. Tau bar 1, 2, this is the one that would come from the same helicity piece. And here there is a non-local term that comes from this mixed helicity bracket. Questions? Yes.
It's interesting that you can write this in some reasonable form using the shadow transformation. A priori, why should we have expected to get anything nice or simple when we started taking brackets of Qs with Q bars?
I wasn't expecting it.
Oh,
I was hoping to get.
you worked awfully hard if you weren't expecting to get it.
Well, I mean, I always feel very uneasy when a commuted and close. And if the symmetry somehow describes real gravitational waves, you would expect that you could be able to mix. I mean, you could have both velocities, right, of a gravitational signal a priori. If you're not able to compute real charges, it would be, or even just the question.
But you could have one algebra that acts on an S matrix, which contains both helicities, right? You don't necessarily need to have.
Well, yes and no, in the sense that yes, you can have a charge X on both felicities. That's true. But I would like to also have a bracket for the mixed helicity, because I can use the bracket to constrain the OPE in the mixed helicity sector, as I want to argue.
If you had got something very simple, you might have succeeded in integrating the Einstein equation.
Oh, this is only up to spin 2, spin 3, of course. This assuming that the recursion relation is still valid at the one I introduced before. So this will not be true anymore at higher spin bigger than 3. Right? It's the same story with the W1 infinity. I mean, in full gravity, that only is be shown to be valid at up to spin equal 3. Right? It would get much worse, probably, if I go higher in spin.
I see. Okay, thank you.
Yeah, so, all right, so this looks promising. Now, let's do the same story for Yang-Mills, where maybe it's a bit simpler, and see what really, how we can use this mixed helicity bracket to say something about the OPE. So again, I think Atul reviewed quite clearly how you do the same construction for Yang-Mills, so I'm not going to spend much time. You can write again a recursion relation for these aspects, which are given by the sublime modes of these components of the strength field. And this recursion relation gives you, allow you to compute these aspects, and then you renormalize them using, again, a linear combination of them. And the soft aspects are, again, now instead of S plus 2, I have S plus 1 derivatives of the soft gluon, the conformally soft gluon operator, which is written in this way here. And introducing smearing function, I can compute charges. Now you can do the mixed helicity bracket of these charges. So you can take R and R bar, again, assuming that one of the two live in the wedge, then the mixed helicity bracket can be written as R bar charge as S plus 1, where again, these parameters here is now not local anymore. It's local, it's not local anymore. Okay, so this would be a shadow charge for this combination of parameters. So there are two no localities. There is this S bar is a bar shadow transformation, and then there is this inverse bar shadow transformation acting on tau bar prime. So a priori, this structure, this commutator is highly non-local. At least it has two propagators in it. But in some cases, this action can become much more localized, as we'll see in a moment. So now, okay, celestial OPE. So the celestial OPE for primary gluons is mixed helicity. Now let's assume I only do the one or more one collinear limit. So I only get a pole here in Z. I will tell you that a priori there should be another contribution if you consider Z and Z bar to be complex conjugate to each other. But let's for the moment forget about that. And you have this this OPE here that has been can be derived again using also symmetry or for instance arguments. Now we know that there is an ambiguity in the mixed helicity sector in which I'll go from this to an OPE that involves two soft gluons. Right, if I take delta 2 or delta 1 going to 1 minus S and 1 minus S prime, at the same time or one before, one the other, we know that we get different answers, which we don't have in the same helicity sector. Now, what I'm going to use to solve this ambiguity is demanding, again, this correspondence between, as I mentioned before, that the OPE of two soft gravitons can be written as the action of the hard charge on the soft graviton. Here I wrote in terms of the soft aspect, but you can replace this object with the soft gluon, and here you will have the soft gluon. The important piece is that you have a soft charge here and a hard charge here, and then you can act on whatever you want. Now, if you demand this also for the mixed helicity sector, then there's only one prescription that is compatible with taking the double soft limit, which is the delta going to soft first, because you see, it's always the first entry that has to be soft so that I can understand this OPE in terms of a hard charge action. And if you do that, in this, for instance, in this case, this is the OPE that you get when you do the double soft limit. So this is the OPE which is consistent with the mixed helicity bracket that I computed before. So there is a prescription, and which also seems to be valid when you also when you treat Z and Z bar as complex conjugate. As I was saying before, there would be extra terms that is appearing in this OPE, but at least for the case where S is more than 1, we know that those extra terms, when you go to take the conformal limit, conformally soft limit goes away, they go away, and the prescription remains the same. So delta, the first entry, has to go soft first. So now we can use that to, with this prescription, we can compute shadows, OPE of shadows operators. So this is what I was mentioning in this paper of Monica and Mina. What they did was to use the OPE block to express, to do the shadow of the OPE block to write down what is the OPE between a shadow operator and a non-shadow operator. The reason why they use the OPE block is because now, since you lose the notion of collinear limit, it's not expected anymore that only the primary term contribute more than the subleading term. So you need to consider the whole family of descendants, and that's what the OPE block does for you. And then basically do a shadow of this OPE block. And this is, for instance, the result that they get when applied to Kirill-Core algebra of soft gluons. Now, an example of this is, let's do a simple example when we have a first spin S equals 0 and the second spin is S equal 1. You apply this, you do the conformally soft limit with the order I told you before, and you get, this is what you get. You get here a shadow conformal primary operators, soft conformal gluons on this side with this 1 over Z pole. Now, this looks a bit suspicious in a sense because you would expect no localities should show up. And in fact, I mean, they do say in the paper that we expect this shadow P block not to capture the full analytic structure of the OPs exactly because we don't know if we are capturing the full singularity structure using these techniques. But we can check the formula with what we did, right? So again, we can write down the celestial diamond for gluons. So here I'm doing now the case where S is smaller than equal than 1. So here instead of the dual gluons, I have the shadow charge. Here I have the soft gluons. This is the shadow of the soft gluons. So now these two are related by a shadow transform, and these two are dual to each other. So using this, you see, using this diamond, I can compute brackets of this guy with this guy, and then doing derivatives or inverting derivatives, I can compute OPEs of these two guys. So this is the idea. And again, demanding the OPE bracket correspondence, this was so this is the OPE from two mixed helicity soft gluons without taking the shadow. Now you can do the shadow. You see, if you do the shadow on the first entry, that was the one I showed you before, all you need to do is to take two derivatives of this object here, and to compute the shadow of F1. And what you obtain from this OPE, you recover the term that they had, But in addition, you start seeing the non-locality in these higher order poles that show up in the OPE. So there is this way somehow the bracket, the mixed helicity bracket, allow you to capture the extra pole analytic structure that would come from the non-locality of the shadow transformation. And I mean, you can do this for at least in the sector where the two spins is smaller than 1. You can do it for like f bar 1 and f tilde s, or vice versa. We know that the relation between the bracket and the OPE is should be exact as soon as one of the two spins is smaller than 1. So this can be extended for the full case. We don't know, because there might be correction to the OPE, which the bracket will only capture once we introduce the correction to the charges. So I wouldn't trust that. But for instance, the lucky thing is that the stress tensor, the CFT stress tensor, is a shadow of a spin 1 object. So a priori, we could be able to compute, for instance, the OPE of two stress tensor in celestial CFT in this way. No, I think actually I'm done. Maybe since there are some extra time, let me just give you an application. Okay, all right. So, okay, let me just give you the outlook, which is very short. Two main messages. So the inclusion of, in general, local shadow charges is really necessary if we want to close the mixed helicity bracket, at least at the linear order. And demanding the celestial P correspondence with the spineless charge, we have a really key entry now in the orographic dictionary, which at least can be either consistency check for OPEs that we are sure about, but at the same time can also give new insights for OPEs of operators that from the celestial point of view might be more murky somehow. And the next main thing to do is definitely check if the algebra structure survives at quadratic order. I would expect that maybe some extra conditions are required in the sense of holomorphicity of the parameters probably are required when we go to quadratic order, as it seems to be the case at least for the 0-1 sector. When you do the mixed helicity 0-1 sector to quadratic order, at least that's what happens. And of course, the question that came up earlier, what's the relevance of this recursion relation in encoding the full Einstein equation when we go to the spin s bigger than 3?
Okay, thank you very much. So we have some time for questions or additional comments.
Yeah, so this is very nice. I have two questions. One quick one, which is at some point you said you have to invert derivatives, and then in principle you get the result up to global information. Is that at all relevant? Because the derivatives along the sides of the diamond annihilate those global pieces.
I think for the highest spin charges, maybe for the Newman-Peros charges, it would, but I would expect that for these local ones in this spherical Morin decomposition, because those maps are injective, this derivative are injective, so I expect that shouldn't be a problem.
Okay, and the other question is that at the end of the day, when we would like to work with one basis that is complete but not overcomplete, right? And working with both operators and the shadows is overcomplete. Do you have any comments on?
I mean, you can choose either basis, right, to express.
Do you have one, because your formula included both operators and shadow operators, do you have one basis where you sort of have one complete but not overcomplete set that includes, I don't know, some operators and some shadow operators?
Well, you can compute, for instance, shadow with shadow in mixed helicity if you want, and that it's something that you can. I mean, if you are in the same helicity and do check, basically recover exactly a very similar formula that you have for the other bases with some some shadows. Here, I think you would just recover the same structure that you have for the other bases with the just putting tildes everywhere, basically, if you're in the same helicity. If you are in the opposite helicity sector, you would get some more non-local structure, of course, also in the shadow bases. The need for using both bases is somehow to talk about real charges. That was my original motivation. I want to really recover just, for instance, GBMS transformations, the real ones, including a dual mass, right? And to do that, you need to talk about both sectors. That's why I start looking into this. And in the case of the OPE, I think it might be relevant to understanding, for instance, maybe like the 2-point function of the stress tensor with the opposite helicities.
Yes, so in the paper with Lionel and Adam, we constructed the charges associated with the other helicity, starting from twistor space. And so it's in the self-dual sector, but then we show that the algebra is closing at all orders and so on. So do you know if your charges are the same, or is there some relation?
I would expect that you can record those charges. My intuition is that self-duality somehow localize all the shadows. Because I guess you didn't get any non-localities in the, at least when you do the bracket, probably, right, of the mixed helicity.
Self-duality.
I would expect that self-duality would localize the action, the bracket, what you get on the right-hand side of the bracket of two mixed helicity sectors. Because you did compute the bracket of two mixed helicity charge, right? And you don't get anything which is non-local.
Well, when you translate the charge on space-time, then you get some non-local expression.
Okay.
But so the charge themselves are non-local when expressed on space-time. They are local on twistor space, but.
Well, I'm not sure if the same notion of non-locality, because here you see, I mean, I can, maybe let me go back a second. You see, I can, so this is okay, this is one sector. Let's say everything here, it's fine, it's local. The taus are local, the aspects are local, I integrate over the sphere. Now, when I can express, the point is that I can express the opposite helicity charge with a local tau as the bar charge where the aspect is local, but the tau now is non-local on the side. So here there are two integrals on the sphere, basically. There's the integral coming from the smearing the aspect against the parameter, but the smearing parameter itself is non-local. That's the difference with this charge. So I'm referring to this kind of non-localities. I don't know if it's the same that you have in the self-dual case.
Yeah, at least it's not, I don't think so. It's not obvious. But...
Yeah.
Other questions? Yes.
I don't know if the question makes sense, but let me ask it anyway. So you have these two towers of charges, Q in one helicity sector, Q bar in another, and then you want to see how they talk to each other, let's say. What is it preserving? Is there some mixed helicity, phase space, or symplectic structure that has been preserved by this full thing now?
For instance, the Ashtiga-Strobel phase space contains both helicities, right?
Yes.
So you want to...
So now this whole algebra, symmetry algebra, is supposed to preserve the Ashtiga-Strobel phase space?
It acts on the full phase space. And well, preserves in the sense that, I mean, the full sector close an algebra. You don't have to restrict only to MHV sector, or in that sense.
So
you can see how one helicity sector act on the other one.
So, I mean, in principle, one could derive these charges from that symplectic structure by
Oh, yeah, you can express all of them in terms of the shear and the news. The aspects, you see, that's the point, that the aspects are the same. I'm just doing a local action on the parameters. So the generators are still the same one that in terms of the news and the shit that I showed you before, with bar or not bar. But the parameters are.
Any other questions? So if not, let's thank Daniele again. And we can go for the coffee break.